This video will cover some of the internal implementation details of the built-in map data type in the Go programming language. When you create a map variable, the variable contains the address of a map header. The map header is a struct with fields to store metadata about the map. The actual data that we store in a map, that is, the key-value pairs, are stored in an array of buckets. The map header contains information like the number of elements in the map, the number of buckets, and a pointer to the bucket array, among other things. Each bucket contains 8 slots. One slot is the memory needed to store one key and its value. Go starts with one bucket. When you add more elements to the map, buckets will become full at some point. A new memory is allocated with twice the current number of buckets. Then data is copied from current buckets to new buckets. The data is not copied all at once but incrementally on each insertion or deletion. Go doesn't wait for all buckets to be completely full before growing the map. The growth is initiated when buckets are around 80% full, which would be an average of 6.5 entries per bucket. The source code for most of the code that we will be discussing in this video can be found on GitHub within this file. Next, we need to understand when we insert a key-value pair, how a bucket is selected, and how one of the 8 slots inside the bucket is chosen. This is where the hash function comes in. A hash function takes a key of any length and returns an integer. Given the same key, the hash function returns the same value. A hash function should also provide a distribution of values. Even if you supply the function with nearly identical keys, the results should be very different. Imagine if we chose a hash function that didn't provide a good distribution of values. Instead, the values it generated are within a small range. In this case, assume the values we insert into the map are going to the same bucket. All other buckets allocated for the map are empty. Then retrieving an element from that bucket will take a longer time and our map operations will be slow. Note that the header type in the HTTP package in the standard library that is used to store HTTP headers of a request is a map data structure. If an attacker is able to choose a list of headers such that they all hash to the same bucket, they could crash our server. Just to see what a hash function does, we can use the map hash package in the standard library. The map hash package doesn't provide hash functions for every data type. The package currently only provides hash functions on byte sequences. There is an open proposal to add a hash function for any comparable type. For a string, you can generate the hash value like this. Another thing to understand about hash functions is that the value these hash functions generate depends on the seed. The map-hash's hash object has an initial seed set automatically. A seed is a random value that selects the specific hash function computed by a hash object. So when the seed is different, they produce wildly different hash values for the same key. Here, each new instance of the map-hash's hash object gets a different initial seed and thus they produce different hash values for the same key. Similarly, when the seed is the same, they produce the same value. Go didn't have generics till version 1.18. However, container data types like maps or slices should support multiple types, which requires generics to implement. So the Go runtime does some magic behind the scenes when you define container data types like maps to give you the feeling that it's a generic data structure. For example, assume our map has string data type as its keys and integer data type as its values. Consider the below operation where you retrieve the value of the key from the map and assign it to a variable. When you compile your program, this single line of code will be translated to function calls defined in the runtime package. First, an unsafe pointer to the key is created. An unsafe pointer represents a pointer to an arbitrary type. An unsafe pointer allows a program to defeat the type system and read and write arbitrary memory. Next, the map access1 function in the runtime package is called, passing a few parameters including the map header and the pointer to the key. This function returns an unsafe pointer to the corresponding value, which is then cast as a pointer to int since the keys of our map are int type. Then this pointer is dereferenced to retrieve the actual value, and it is stored in the value variable. The function definition of this map access function is defined in src/runtime/map.go file. Similar to this, all other map operations are compiled into different function calls in the runtime package. As you can see, all of these functions take a pointer to a map type and a pointer to hmap. The hmap is the map header struct that we saw earlier. It stores metadata about the map, including the number of elements in the map, a pointer to the buckets where key-value pairs are stored, and a hash seed. A new hmap struct will be created for every map that you define in your program. And every one of those hmap structs will have a different random hash seed value. Another type that's passed to the runtime functions is the first argument, which is a pointer to a map type. You might be wondering why we need a map type when we already have an hmap. An hmap is the map header. A unique value of hmap gets created for every map that we create. A map type value is only created for each unique map declaration in your program. For example, in your program, if you are creating 3 maps that map from strings to integers, there will be 3 hmap values. There will be only one map type value that represents a map from strings to integers. The map type helps in making the hmap struct generic for any combination of key and value types. As you can see, the type of some of the fields of the map type is _type. This is called the type descriptor. The type descriptor contains important pieces of information like the size of the data type it represents, what kind of data type it is it a struct or int, which is important because the buckets of the map don't always store the key or value directly. For some data types, the map stores pointers to the key and values. Next, let's look into the implementation of the map assign function, which gets called when you store a new value for a key in the map. First, we generate the hash value for our key that needs to be inserted. Then we apply a mask to the bottom bits of the hash to identify the index of the bucket in which the key needs to be inserted. The first parameter t is a pointer to the map type. The map type is the one that gets created only once for each map type. It also contains a hash function for hashing its keys. The second parameter h is the map header. It defines the hash seed that will be used to hash its keys. A new hmap value gets created for every map that you create in your program. So every map will have a different hash seed. This means the hashes generated for the same key will be different in different maps in your program. Next, we do some bit masking on the hash value to identify the bucket in which the key and value should be inserted. Assume that we have 8 buckets allocated. So h.b will be the log of 8, which is 3. The bucket mask function does some left shift operation which is essentially equivalent to computing 2 to the power n, which will be the total number of buckets allocated for the map. Then we decrement the value by 1. Then this value is used as a mask. Doing this bitwise, an operation returns a value between 0 and 7. Now that we got the index number of the bucket, we need to find the starting address of the memory allocated for this bucket. For that, we do some pointer arithmetic. The bucket number is multiplied by the size of an individual bucket, and this value is added to the starting address of the memory allocated for the array of buckets. The final step is to iterate over the cells in the bucket until we find a free slot and insert our key and value there. If the key was already present, we would overwrite the value. To understand this iteration procedure in more detail, we need to understand the data structure that represents a bucket. As you can see from the comments, the actual key and value are not represented directly in the struct. This is because the type of key and value that we store in a map can be of any type. So the compiler cannot know what the size of the bmap struct should be. If you were to create a map with strings as keys and integers as values, you can imagine the bmap struct like this. The top hash field is an array of 8 elements. It contains the top byte of the hash value for each key in that bucket. For example, the third element in the array will be the top byte of the hash of the key that is stored in the third slot of this bucket. Before iterating over the elements in the bucket, we first compute the top hash value for the key that we are trying to insert. So if this was the hash value for our key, its binary representation will be this. and the top hash of it is its first or top byte. This is the actual code for the top hash function. Here we do a right shift operation to get the first byte. There are some predefined values for the top hash value. You should be able to understand their purpose by reading the comments. The iteration happens like this. This is a simplified version of the actual code. The initial part is the code that we already discussed, where we identify the starting memory address of the bucket in which we will be inserting the key and its value. Then we compute the top hash value for the hash of our key. Next, we iterate over the 8 slots in the current bucket. Instead of comparing the entire key, we compare the top hash value of that slot with the top hash value of our key. If the top hashes are not the same, we continue checking the next slot. If there is a free slot, we keep track of that free slot so that we can insert the key and value there if the key was not previously inserted in some other slot. If the top hashes are the same, that could be the index of the memory slot where the key was stored previously. To get the address of the memory where the key is stored, we do some pointer arithmetic. We multiply the index we identified with the size of the individual key. Then we add the value of the data offset to it. Data offset is the size of the bmap struct itself. This value is added to the starting address of the bucket to get the address of the memory where the key is stored. Then we compare if the key that is already stored in that memory location is the same as the key we are trying to insert. If so, the value will be overwritten in the slot corresponding to this key. Computing the memory address where the value should be stored is similar to how we did it for the key. Since the memory for the bucket is allocated in such a way that we store all keys first, then all values after that. So from the starting address of the bucket, we need to skip the memory for the top hash array and the memory allocated for 8 keys. There's more code to allocate an overflow bucket if the current bucket and overflow buckets connected to it are already full.